Hey everybody, this is 7.2, Day 2, Part 1. So we're going to continue working with those exponent properties and the radical properties like we did yesterday, and today the focus is more on the radicals. So first I want to talk a little bit about what it looks like if you're trying to add some like terms with radicals. So quick review, like terms. Two things that have the same variable with the same exponent. So for example, x and 2x would be like terms. Here's another example. Xy squared and 3xy squared would be like terms. Same variables, same exponents. Also, comment, xy squared and y squared x are like terms because when I multiply, you can write it in any order and you get the same answer. For radicals, like radicals, have the same index and radicand. The radicand is the number underneath the radical. So if I said the cubed root of x, 3 is the index and x is the radicand. Alright, so to make like radicals, the cubed root of x would be a like radical term with something such as 2 cubed roots of x. And just like how I could add together x plus 2x, I can add together 1 cubed root of x plus 2 cubed root of x's, and that would equal 3 cubed root of x's total. So like terms with radicals has to have the same index, same radicand, and the number in front might be different. Here's another example. You can also have like radicals if you have a number underneath. So let's say I had 3 fourth roots of 2 plus 4 fourth roots of 2. That would equal 7 fourth roots of 2 total. So you treat the radical just like a variable and you don't change it, only the number in front. When we're adding, when we're multiplying, something different happens, but when we're adding or subtracting, just the number in front changes. You also can have more than one thing underneath the radical. So my last example here, let's say I had the fifth root of 6x. That would be a like radical term with something else that has the fifth root of 6x. As long as this whole part is the same, then I could add or subtract those together. Also, this is kind of weird, but I can have like terms with power statements. So let's say I had 2 to the 1/2 power plus 4 times 2 to the 1/2 power. This is really like 1 2 to the 1/2 powers plus 4 2 to the 1/2 powers, and that would be 5 2 to the 1/2 powers total. So let's do some examples with this. We're going to simplify and we're trying to combine like terms here. So these first few are just like the easy ones I showed you. So here I've got 2 cubed roots of 3, subtract 5 cube roots of 3, and that would be -3 cubed roots of 3 total. Next I've got 8 minus 2, and my quote variable is 6 to the 3/4 power. So that means I've got 6 of those things, those variables. Now in this situation we're just working on adding like terms. So if you left it like that, I would give you full credit, but in this situation, because these both have the same base, technically I could use those exponent properties we learned the other day and add together my exponents. So this is really, if I combine it, 6 to the 7/4 power. Alright, next. Again, if there's nothing in front of a radical for part C here, remember it's really like a 1, just like how x is really 1x. So here I've got 1 of those plus 7 of those, so 8 of those total. Alright, for lots of these problems there's more than one way you could go about doing them. So what I'm going to show you is one possible method, and you could do things in a slightly different order and still get the same answer. So right now what I'm going to do with example D, I'm going to use that property we learned where if it is multiplying inside, if and only if it is multiplying or dividing inside a parentheses, I can distribute the exponents. So now I've got x to the 1/2 power times, and then when I do power to a power, remember I'm multiplying, so 1/4 times 1/2. Okay, that new power is 1/8. And then last but not least, I'm going to combine these by adding the exponents. So 1/2 plus 1/8 when I'm multiplying exponents like this. Looks like I think I'm going to have 4/8 plus 1/8, so my final answer is x to the 5/8 power. Next problem. When I have that fourth root like that, I can split this up. And by the way, some of these are not like term problems, just different, I guess D and E I just kind of threw in here for extra practice. I can split up this, remember, the root with a fraction underneath. And what's happening here is that a fourth root is the same thing as a 1/4 exponent. So really, I have this on top, and I have this on bottom. And then you can multiply your exponents. And here, 8 times 1/4 is 2, and on bottom, 4 times 1/4 is 1. All right. So F, G, H, and I are all more combined like term problems. And then I want to tell you that they're not always going to make it super easy like A, B, and C were. For these ones, we're trying to combine like terms, but I do not have the same radicand. Remember, radicand is the number underneath. I don't have the same radicand. So what that usually means is I need to do some sort of simplifying, and most likely I will get to the same radicand after I simplify. The book has created these problems so that they work out nicely. So the first thing you want to do is use that upside down division we learned and go ahead and simplify the cubed root of 16. So I'm going to go through, remember, divide by a prime number. Don't have to start with the lowest, but in this case I'm going to start with 2. I'm going to keep dividing, and then I have a cubed root, so I need a group of 3 to put 1 in front, and then I have 2 left over, so I've got a 2 underneath the radical still. And voila, now they are like terms. And remember, if there's nothing in front of this radical here, it's really a 1. So now I've got 2 subtract 1, so I have 1 cubed roots of 2, or just cubed roots of 2. G is kind of another easy one, actually. Again, just remember, if there's nothing in front, it's like a -1. -1 plus 7 is 6/8 roots of x. All right, H is another problem where we're going to have to do some work. Why don't you pause the video and give it a try? If you're unpausing right now, you should have gotten the cubed root of 625 is 5 cubed roots of 5, and so your final answer for this one is 4 cubed roots of 5. Why don't you try I as well? Pause and try I. Okay, your final answer should be -3gh to the 1/4, and just, they're trying to trick you again, but this entire thing is the quote variable, so all I worry about is 3 subtract 6, and then that variable just stays as is. Alright, this next part, we're going to do some simplifying with radicals, with exponents underneath different index numbers for our radical. And so this is a little tricky, so pay close attention and write down some questions that you might have that you want to ask me after watching this. Alright, so here's an example. Let's suppose that I'm trying to simplify the square root of x to the 5th. Basically, we want to pull out any variables that we can. So I just want to remind you back to, let's say I had the square root of 27. We split that into the square root of 9 times 3, but really we split that into the square root of 3 squared because the square root and the square cancel each other, if you remember. Same thing applies if I have variables underneath. So here's what I mean. I want to rewrite x to the 5th so that I have groups that are going to cancel out the square root. And to cancel out a square root, you need a group of 2. So when I think about the number 5, there's 2 groups of 2, and then there's 1 group of 1 left over. And what's happening here is that, remember our property, these can all split up, so it's really like the square root of x squared times the square root of x squared times the square root of x to the 1st. And again, the reason I do that is because the square root and the square are going to cancel each other. So now I've got x times the square root of x, and really that is x squared square root of x, and that is my final simplified answer. Let me show you one with a different index. Now I've got the cubed root of x to the 6. So now, because it's a cubed root, in order to cancel out a cubed root, I need a group of 3. So I want to rewrite 6, x to the 6, so it has groups of 3. And when I'm doing this, I'm thinking adding, because remember, when I multiply the bases, actually you add the exponents. Okay, so x to the 6 is the same thing as x cubed times x cubed. And when I do that, again, I wanted to write it that way so that the cube undoes the cubed root. That's just x times x, so my final answer for that one is just x squared. There's nothing left over underneath. We'll do one more and then we'll do some more complicated ones. This time I've got the fourth root of x to the seventh. And so again, whatever the index is, that's the group size you're looking for. And so now I'm looking for groups of 4. So I'm going to go like this. 7 is 4 plus 3. All right. If you think about this part, that's just going to be x. And this part here is going to be left with x cubed underneath the fourth root. And now there is a shortcut that you can take, and I'll try to say that as we go along. Some of you may already can see what the shortcut is. But let's do some more complicated problems. So we're going to get problems similar to this, only we're also going to have numbers underneath. So when I try to simplify this, for the numbers, do the same thing you normally would. And actually this first example, I just took the first example we did earlier and just put a 25 under there. So this part, the square root of x to the fifth, that's what we just did up there. So that we found out was x squared square root of x. And I wanted to show you that the number part do separately and do the normal rule. So usually you do upside down division and go through it. We know the square root of 25 though anyways, so we can just say that is 5. And usually you write it in this order with your number in front, then the variable, then the square root, and then you'd put a number, and then the square, and then the variable, and so on. All right, let's do part B. So again, split it up so that the number is going to be separate. And so I want to think about what goes into 8. I can divide by 2, and because I'm taking a square root, I'm looking for groups of 2. So I've got a 2 I can put in front, and then I'm going to have a 2 left over. And again, the numbers always go first, and then the variables come afterwards, so I'll leave some space. All right, now I got to split up the square root of x cubed and the square root of y to the 6. So again, I'm doing a square root, so I'm looking for groups of 2. So it looks like I'm going to have one group of 2 that I can cancel with the square root and one left over for the x's. For the y's, it looks like I have 3 different groups of 2, and when I pull out 3 groups of 2, I don't have anything left over, so 2xy cubed square root of 2x is the answer. And now maybe some of you are seeing a shortcut here. The shortcut is, and you don't have to use a shortcut, you can always write it out if you want to, but if you look at this, whatever this power is, you basically divide it, so 3 divided by 2 is 1, with a remainder of 1. So however many times it divides is the outside exponent, the remainder is the inside exponent. So let's look at the y's. 6 divided by 2 is 3, outside exponent. No remainder, that was the inside exponent, but we didn't write it down because there was nothing. I'll apply that shortcut to the part C so you can see how it works a little better. And again, if the shortcut is really confusing you, you don't have to use it. It's optional. All right. Let me do the numbers first again though quick. So I'm trying to figure out the square root of 32. I'm going to be looking for groups of 2 again, but I'm going to go through my upside down division. Alright, I've got 2 different groups of 2 that go in front, and then it looks like I've got 1, 2 left, so that'll go underneath. Alright. So let's use that shortcut and I'll say more. So again, the index right now is 2. So I'll look at my a to the 8th first. Here's what I'm doing. 8 divided by 2 is 4, so that's my outside exponent. And then there's a remainder of 0 when I do 8 divided by 2, so there's nothing underneath. For the b's, 2 divided by 2 is 1. There's no remainder, so there's nothing underneath. For the c's, 7 divided by 2 is 3. And then there's 1 left over, so I'll put 1 underneath. So let me write this a little bit nicer. And now, if that didn't really make sense to you, just pause the video and try doing it the long way where you write it out, and you should get the same answer. As soon as you have all that down, flip to the back, and then we're going to go to the second video for this section.